And make sure it does have audio because I definitely recorded a Discord screen share presentation and then realized after 2 hours that it didn't have any audio.
Yeah, it has audio. Since I'm not using my headphones though, it's picking up my speakers through my headphones, and Discord doesn't normally filters that out. So I want to connect my headphones, but ever since I connected my headphones to my new phone, the button on the side no longer lets me switch off noise canceling, and I hate noise canceling if I'm not like on an airplane or something.
I
So
also hate noise canceling. I don't know how people just use it all the time.
yeah, I used like when I first had those headphones, it was awesome, and then I started to hate it. So I there might be
It's
like a
very
little bit of an
disorienting.
echo in the recording, but I guess whoever is watching it can deal with it. Yay.
This will cure you.
Oops.
Langston, do you think those are gunshots or fireworks?
Those sound like fireworks.
Okay. Is Maddie joining?
I don't know.
You want to promote? I feel like, Ben, you haven't promoted this.
I did ping her.
You want to promote this in the WoW Savage?
I don't really know if I need to promote it.
I just feel like, more people hearing it means more blessings.
Well, the PDF is now, I mean, built, so if I ever feel like it, I can just give the talk again. It's not that big of a deal.
Why are the things on the top, why are there different... Oh, is that the difficulty level?
No, those are the sections.
Why are they in that order?
Because it's the order I decided to put everything in.
But like the O's on the bottom, why is it like one O and then it's six
Oh,
O's and then
those are
it's
the
four O's?
slides. The slides, yeah.
Oh, I thought, okay, you should definitely add a difficulty level. That's pretty funny. Like when they put like spiciness levels on a menu, you need that. Actually, you should just put spiciness level
Yeah, I should
for the
label
future,
it.
of course. Mm-hmm.
Well, I don't necessarily want it to get harder and harder, but maybe that is what ended up happening. I don't know. We'll see. I also like built maybe like half of this today. So I don't know, like, oh, you can see my mouse. Okay, that's good because then I can point to things.
Yes. Wait, are you recording yet?
Yes, it's recording.
Oh, why is it already recording?
um, I don't know. I didn't know when I was gonna start, so
Okay, I'm co-opting it.
you're wait. You're recording
Oh my
through
god.
Discord?
Oh
No,
my
I'm
god.
co-opting the video.
Oh, I
That's a
can't see
cat.
it.
That is a cat.
There he is. Look, you can turn your mic on because, like Abigail said, it's gonna cure you anyways. So
Okay.
it won't matter.
Can you hear me?
Yes.
No, Dick Jordan heal. Don't don't make Jordan talk.
No, Jordan, you have to
Okay.
ask questions. This is important.
Did you not hear this man? He sounded so sick, and I've never heard someone sound that discernibly sick from saying hello.
Yeah, that was crazy.
I'm okay. I'm just not thinking, probably. I'm not smart. Hold on.
Then you'll
That's okay, because
be
it's for
asking
noobs.
lots of questions, right? That's good. I need people
Says
asking
it's for
questions.
noobs. It better be for noobs.
I
I
tried.
actually do have a question before we start.
Okay, yeah. We can start after your question.
Langston said division is not real. Can you explain
What?
what that means?
Yeah, I can explain it. It's like during the talk actually.
Oh,
Like
okay.
what
We'll
he
stay
means by
tuned.
that. Yeah. Okay, yeah. So in this talk, I'm basically going to try to describe what my thesis is probably going to be on. And so it's about ordinal graph C-star algebras. It's not about that for noobs, but this presentation is about that for noobs. And so I'm going to start by describing C-star algebras and then ordinal graphs. And somewhere in the middle, I didn't actually define the ordinal graph C-star algebras, but hopefully by the end it will be pretty clear how they're defined. And I kind of just ran out of time too, so I didn't add those slides. But anyways, so the way so I study C-star algebras. It's a field of math called operator algebras. There's lots of intersection between operator algebras and different areas like physics, mathematical physics, really, analysis, and algebra. And operator algebras kind of sits in this crazy intersection between all these different areas of math. I could even have another circle in here for combinatorics because a lot of what I'm going to be talking about is actually combinatorial. Okay, and yeah, seriously, if you have questions, just ask them during the talk. I don't mind at all because the whole point is that, like, I'm answering your guys' questions to begin with. So, okay. C-star algebras actually came from quantum mechanics. So, operators algebras in general were invented to study quantum mechanics. So that's what I'm going to be using to motivate C-star algebras because I'm not assuming that you've seen any linear algebra or anything. So quantum mechanics is basically the physics of really, really tiny things. And a bunch of behaviors in classical physics are really there's a bunch of behaviors of classical physics that break down on that scale. So things are quite different. Let me explain. Okay. Basically, if you have some physical system that you're talking about, so if you're doing physics, essentially, and you want to simulate that system, you need some information about it. And you could say that the state of that system is all the information you need to simulate it. So classically, you could have maybe a particle bouncing around in a box, and the state of that system would be the position and momentum of that particle. And then knowing those two things would tell you how to simulate the trajectory. And once you know the trajectory, you know where it bounces. So you can simulate the system. Now, in quantum mechanics, the state of a system is a vector in a Hilbert space. So this is for noobs, so I'm not assuming that people know what a Hilbert space is, but think of vectors as things you can add together, and you can also multiply the vector by a constant. So generally when you learn about vectors in Calc 3, they're used to represent directions. And that's fine. So you can add directions and you can multiply directions by constants that ends up scaling the arrows. But here we're using complex numbers, so it no longer really makes sense to think of vector solely as a direction in Euclidean space. So just think of these abstractly as things that you can add together and multiply by some constants, and our constants will always be complex numbers. And then really all you need to know is that there's this thing called an inner product between vectors, and when you take the inner product between vectors, you get some complex number, and you write that with these angled brackets. So if I have two vectors, v and w, these might represent two states of some quantum system, and I take the inner product, I would write that using these angled brackets. And if you've seen vectors before, you know that you can compute the length of a vector, and you can, for a Hilbert space, you can give vectors a length using this inner product, where you define the length of the vector v to be the square root of the inner product between v and itself. And because of properties of inner products, which I haven't defined what an inner product actually is, but because of properties of inner products, this is always a positive number. So it's telling you basically how big the vector is, abstract, but in some weird abstract sense instead. So
You can know how an inner product is done later, or no?
I can give an example later, I guess.
Okay.
I would also find that helpful.
Yeah,
I think I did it. I just forget it. So.
Yeah, so I can give an example, but I'm kind of just going into this like thinking that people haven't seen inner products to begin with anyways. So like at that point, trying to motivate them without doing a whole bunch of other math seemed kind of pointless. But yeah, so let's see. If I get to the end of this section and I haven't found a convenient place to give an example, I'll just give you guys an example, okay?
That's fair.
Are inner products commutative?
No. If you
Okay.
it's actually interesting. If you take the inner product between v and w, you get some complex number. And then if you take the inner product between w and v, you get the complex conjugate. That's like one of the defining properties of the inner product.
Okay. Cool.
So
Didn't you do it in Calc 3? You did, right?
in Calc 3, you compute the inner product between vectors, but they're you use the dot product, right?
Yeah.
But those are real vector spaces, so you're not multiplying things by complex numbers.
Factor.
Right.
Yeah.
So instead
Right. Okay.
Instead of multiplying the entries and adding them together, one of them you take complex conjugates of each thing.
Gotcha.
Yeah. But
Makes sense.
yeah. Okay, so in quantum mechanics, when you're modeling quantum mechanics with math, you represent the quantities that you can observe as objects that physicists call observables. So you could think of some classical system where you have a particle bouncing around in a box, say, or maybe not even bouncing, just moving. And the position of the particle is an observable. And you can still think about such a system in quantum mechanics. So you have a particle moving, its position is still an observable, and that observable is usually labeled V. So we have this, for a quantum system, we have this Hilbert space, which I'm always going to call h. And the weird thing that quantum mechanics does is it assigns to each observable a special operator on the Hilbert space. So now I have to tell you what an operator is, but I'm not going to be formally defining most of the things in this section. So an operator, you can think of an operator as a function which takes vectors in the Hilbert space and gives you a new vector. So if I have an operator t and a vector v in my Hilbert space, then I can write down the new vector that the operator gives me as tv. So when I write tv, that's what I mean. You're plugging in the vector into the operator. And if you know what this means, these operators are linear. So basically they respect addition and they respect multiplication by constants. And part of quantum mechanics is knowing how to take some classical system and assign these operators to all your different observables in a way that what I'm about to tell you ends up describing the quantum system. So, okay, so you can talk about an observable now, and when I say observable, I mean operator. So you can this special type of operator, which I haven't told you what special means, but so you can have an observable and a vector v, which represents the current state of the quantum system, and then the mathematical model of quantum mechanics allows you to say what happens when an outside observer measures the value for the observable t. Basically, you can, when classically on the larger scale, if you're observing an object, you can do it without really influencing that object very much. So, like, I'm looking down at my keyboard right now, and the only reason I can see the keyboard is because light is bouncing off of my keyboard and into my eye. So in order to observe the keyboard, the light is having to bounce off of the keyboard. But in quantum mechanics, things are so small that being able to observe the system requires that you disturb it.
Wait, when you say things are so small, sorry, I'm jumping in with actual noob questions.
Yeah.
Why
questions.
are things smaller in quantum mechanics? Like, why is it not things the size of your keyboard that are being studied? What are they looking at that's so small?
So, you could study things the size of my keyboard, but quantum mechanics differs from classical mechanics when things are really small. That's sort of the idea. So when things are really small, things behave unintuitively, but on larger scale, all of this unintuitive behavior somehow averages out and you get something that's more intuitive.
Do you have any examples of things that are this small, or are they theoretical?
Oh, like, if you can think of you can look up the double slit experiment, where they're basically shooting individual particles and measuring them one at a time versus...
Okay, so that's what we mean when we say small.
Yeah, like something like an electron is certainly small enough. Anything like on the atomic scale is small enough. Does that make sense?
Yeah, that does. Thanks.
Okay, cool. So then I can sort of give you an application of the inner product in these operators. So suppose you have an observable t and your system is in a state v, so this vector in your Hilbert space, then you can actually compute the expected value for that observable. So basically, if you were to repeat this experiment a bunch of times and average out the results you get from measuring that value, The math model tells you how to compute the expected value for that observable. So you take v, plug it into your operator, and then take the inner product with v, and this is the average value for that observable. So lots of people who study quantum mechanics, they just want to understand the observables of a system. And so observables are operators, so really, it suffices to understand operators. But operators are very complicated objects, especially when your Hilbert space is big. So that's easier said than done. There's this special family of operators which we call bounded operators, and these are sort of operators which are a lot easier to work with mathematically. And so I'll be if you've taken calc, what this actually, you can sort of imagine what I mean by this. The bounded operators, what this actually means, it's the collection of all operators which are continuous on your Hilbert space. So the collection of all bounded operators on the Hilbert space, call it B of H. B of H is the first example we've seen of a C-star algebra. Okay, so now I need to motivate the definition of a C-star algebra, right? So if you have two operators S and T on some Hilbert space H, then you can add the operators. And the way you add the operators, you say that the sum between S and T applied to a vector V, so S plus T needs to be a new operator, and it's the operator such that when you apply it to V, you get the vector SV plus TV. So applying V to S plus T is the same as first applying V to S, then applying V to T, and then adding them together. And you can also multiply operators by a constant. So you can say that constant is lambda, and then lambda S, it needs to be another operator, and it's the operator which takes the vector V and returns lambda times S applied to V. And you can also multiply operators together. So operator multiplication is function composition. If you have operators S and T, and you want ST to be an operator, so ST applied to V, you get this vector by first applying T to V and then applying S to that result. So you basically first plug it into T and then plug it into S.
Sorry, just really quick. I think you mentioned this before. Operators have to be linear, right?
Yes.
Okay.
Yeah. These are all linear. This multiplication, though, in general, I was considering unbounded operators before, so like things that aren't continuous, and a lot of physicists will work with unbounded operators. So you actually have to be careful with unbounded operators in multiplication. So there's lots of things I'm just sweeping under the rug, right? But okay, and you can also take adjoints. So the adjoint is, and it's not clear that such an operator exists. I'm not claiming that it's clear, but you can prove that it exists, and it's the unique operator which satisfies this identity. So when you take the inner product, so I'll say S star for the adjoint of S, and that's how we write it. So when you take the inner product between V and S star of W, it's the same as taking the inner product between S of V and W. So the adjoint, you can think of it as allowing you to move the S over, but you have to add the star.
So that's like to counteract what you were saying by it not being commutative.
Yeah. So, right. If
That's
this
how
was
you would do it.
commutative, then if
You need the star. Yeah.
Yeah, if this was commutative, then S star would be S, but it's not, right?
Gotcha.
Adjoints are very important. So, now, before when I introduced observables, I told you that they're really a special class of operators, and this is what I meant. So, you call an operator S and I'm putting in parentheses, complex valued observable. So what I mean by that is it's representing some value of your quantum system which is a complex number, not necessarily a real number. It's an observable if S star times S is equal to S star. You can think about why you would need this, right? So I can give you a pretty good reason why you would want this. If you have an observable S, you can take the adjoint, you get another observable S star, which represents the complex conjugate of the value you would measure for S. Now, if you go back to computing the expected value, you can see it involves this inner product, right? So, when you compute this inner product, so T could be any observable, but it turns out in quantum mechanics you can't just measure. In classical mechanics, you can take a particle and measure the position and momentum at the same time. So you can measure the position. It won't affect the system because it's big enough. And then you can measure the momentum. It won't affect the system. And if you do those things close enough together in time, you've basically measured the position and momentum at the same time. In quantum mechanics, that couldn't be farther from the truth. If you measure the position, then you measure the momentum, you'll get something completely different than if you measure the momentum first and then measure the position. It's pretty strange. But if you could measure two things at the same time, you can measure their product at the same time. So, for example, classically, if I wanted to measure the product between the position and the momentum, I could measure the position, measure the momentum, and then multiply them together. In quantum mechanics, the observable for the product is the product of the observables. So if I have two observables, S and T, and I want to measure the product, then that observable for the product would be S times T. But then you can see that if S times T is different from T times S, when I go to measure the value, I'll get different results if S times T is not equal to T times S. So you can measure two quantities at the same time exactly when the observables commute. So when S times T is equal to T times S. And really what this condition is telling you, it's saying that you should be able to measure the value and its complex conjugate at the same time. And when you can do that, that tells you what the real and imaginary components are. So yeah, I guess it's kind of a complicated explanation, but at least this is necessary. Okay. And a lot of physicists instead will take their observables to be real valued, in which case you require S to be equal to S star instead. So if you have a complex number and you take its conjugate and you get the same complex number, then it's really a real number. And that's what this condition is saying. So if S is equal to S star, we call that operator self-adjoint. And if S in S star commute, we call it a normal operator. So normal operators represent the complex valued observables, and self-adjoint operators represent the real valued observables. And yes, so with this last point, I just wanted to clarify that if you have a normal operator, then you can break it up into the real and imaginary components, and those commute. So really, you can think of either normal operators, or it does no harm to just think of all observables as real valued, like the physicists do. Okay, and yeah, so if you have observables, you can sum the observables. You can always sum the observables and get an observable. And that represents measuring the sum of the quantities. But you can't always measure the product. And if you can measure the product, you can only measure the product when the two observables commute. And when they do commute, then you can take the product of the observables, and that represents measuring the product of the values. And then, like I said, the adjoint represents measuring the complex conjugate of an observable. So that's my crash course in quantum mechanics. Even though this doesn't really tell you anything about how to actually run like a simulation or something, it doesn't tell you how you choose your observables, or how the system actually changes over time. This is mathematically is the setting for quantum mechanics. So before I go on, are there any more questions? Okay.
Nope.
Cool.
You're bringing me back.
Well, bringing you back. That's good. That's what I wanted.
Yeah,
to do.
I'm not being brought back to anything in particular, unfortunately.
Well, the good thing is you don't need to understand the details. So,
That was not a reference to your explanation. I'm just saying I have no mathematical background that this is
yeah,
in
that's
any
okay.
way reminiscent of. But I'm following.
I designed the section so that you could follow it without knowing anything about it. Maybe follow it a little bit without knowing anything about it. Okay. So this brings us to C-star algebras, which I mentioned are invented more or less to study quantum mechanics. And they actually abstract away a lot of the stuff that I was talking about before. So what is a C-star algebra? Well, formally, here's where I'm going to spew out a bunch of words, but I won't be precise in defining any of this. So it's a Banach star algebra which satisfies the C-star identity. So the algebra part just means you can add and multiply things together and multiply them by complex numbers. And star, because you have this star operation. So if you have a C-star algebra and two elements A and B and some complex number lambda, now here is the first time I use this symbol. I'll be using it more throughout the talk. It means member of. So A and B are a member of the C-star algebra A, and lambda is a member of, and then this boldface C is the complex numbers. So whenever we have two elements of our C-star algebra and some constant lambda, we can multiply the element A of our algebra by the constant lambda and get lambda A, which is again a member of our C-star algebra. We can multiply A and B together to get AB, which is a member of our C-star algebra. We can add them together to get another member. We can take the adjoint of A to get A star, which belongs to our C-star algebra. We can compute the norm of A to get some real number. That's what this bold-faced R means. So the norm of A is a member of the real numbers. And real numbers, these are again, just complex numbers, but they don't have an imaginary component. So you can put them on a number line. They're the ordinary numbers that most people are most familiar with. And then this C-star identity somehow, when you study the theory of C-star algebras, this one identity causes a bunch of really nice things to happen, like, and some really deep theorems to appear. It just says that the norm of A star A is equal to the norm of A squared. And now I haven't given you a definition for how you multiply things, or how you take the norm, or how you take the adjoint. Because before, for Hilbert spaces, I told you how you define the adjoint of an operator. But the point is that the definition for a C-star algebra doesn't assume that you have any way necessarily of computing these things. It just assumes that you can add or multiply by a constant, or take norms. And of course there are other things you need to have happen by definition for it to be a C-star algebra, but these are algebraically the things you can do. So you can add, multiply, take adjoints, take norms. Now, I can now tell you an example of a C-star algebra in which you will know how to multiply and add and take adjoints and norms. And it's the complex numbers themselves. They're the most fundamental C-star algebra. This adjoint you just do by taking the complex conjugate, and the norm of the complex number C is the absolute value of that complex number. And notice that this C-star identity, for the C-star identity, when you take the complex conjugate of Z and multiply it by Z, you get the absolute value of Z squared. And so this C-star identity is kind of like reminiscent of that property. In fact, it is what makes the complex numbers a C-star algebra. And so it's actually one nice way of thinking of C-star algebras is just as generalizations of complex numbers. Now, Abigail had a question. Apparently Langston said that division doesn't really exist. And Abigail wanted me to explain that. So this is the appropriate moment to explain that C-star algebras, while you can think of them as generalizations of complex numbers, they're not assumed to have any sort of division. So really, when you have division, what it means is you can multiply an element A by an element 1 over A, say in whatever algebra you have, and get 1, which is a unit. 1 is the special number which, when you multiply it with other things, doesn't change the element. So a C-star algebra could have a unit, and it could, if you have an element A of your C-star algebra, it could have an element B, such that when you multiply A times B, you get the number 1, the unit in your C-star algebra. And then B, you would write B as A inverse, or 1 over A if you like. And you have division really whenever you always have a 1 over A for every possible A. And then division just means multiplying by 1 over A. Does that make sense, Abigail?
I'm so sorry. I was trying to figure out how to use the soundboard, but yeah, it makes sense.
Okay. Cool. Yeah, so in that sense, division doesn't exist. Really, though, I think the truth is it's just helpful to stop requiring division to exist. It allows you to model more things. Okay. So examples of C-star algebras. The complex numbers. The bounded operators on H for every Hilbert space H. H can be some huge Hilbert space. You take the collection of all continuous linear operators on H, and you get a C-star algebra by taking the star to be adjoints, for example. Another good example of a C-star algebra is C0 of X. So this is notation. The C means continuous. The X is representing some locally compact space. What does that mean? It's just basically think of like either a number line or maybe points on a plane. Just think of these as some points somewhere in some abstract setting. Now, what you do is you take functions which take things in X and give you complex numbers. So if you're thinking about the number line, you maybe X is the closed interval from 0 to 1. You take all the functions which, given a number in that closed interval, give you a complex number. So these are the complex valued functions on the interval from 0 to 1. The C is saying that they need to be continuous. So I guess I'm not defining continuous, but if you've taken calc, you can guess how that might be defined, although things are a little bit different because of complex numbers, etc. But, really the intuitive notion of continuity here, where when you change the input a little bit, the output doesn't change very much. That's exactly what continuity means here. And then the 0 means that you require, and this is maybe a tricky thing to see that this is even well defined. You require the functions as you go farther and farther out to vanish, to approach 0. That's what C0 means. So these functions, in that sense, they decay as you move farther and farther away. And that's special, right? Most functions don't do that. So you take all of that collection. Question?
They go away, or they like cease to exist away from 0? Is that what you said?
So the function doesn't cease to exist.
Right.
The values don't go.
The values
aren't equal to 0, but they approach 0 as you move farther and farther out. It's kind of like if you were
farther and farther out, you mean like
if you're on a number line, then it's exactly
like
what you'd imagine,
0, right?
Yes. If you're on a number line, it means that the limit as x approaches infinity of the function is 0, and the limit as x approaches negative infinity of the function is 0. That's exactly what it means on a number line. But
Gotcha.
I'm trying to allude to the fact that it's actually quite amazing in what generality you can define these things. X can really be much more interesting than a number line. Anyways,
it could be multiple dimensional or something.
Could be high dimensional, or could be non-Euclidean, right? So
yeah.
Well, I guess that isn't really well defined here, but it doesn't matter. Anyways, so right, how is this a C-star algebra? Really, you multiply pointwise and you add pointwise and you take complex conjugates pointwise. So if you don't know what pointwise means, it means that, for example, if you were to take the sum of two functions, you plug it in, you plug your point into the first function, plug your point into the second function, add the results, and that gives you your new function, which is the sum of the functions. It's the same function you'd get by if you happened to have a formula for the function, which there doesn't have to be the case, right? But if you happen to have or be able to write down a formula for the function, it's the same function you get by writing down the first formula, putting a plus, and then writing down the second formula. So it's exactly what you'd expect, from algebra class, right? take the function x squared, add it with the function x, that function is x squared plus x. So, okay. Yeah, and taking adjoints here is taking complex conjugates. And everything happens pointwise. And notice that this is commutative. So if I take f times g, it's the same thing as g times f. And because of some deep-ish C-star algebra theory, every single C-star algebra which is commutative is actually of this form, C0 of x, for some space x. So that's pretty cool. These are the ones where everything commutes. But lots more interesting things happen when things don't commute. So if everything always commuted, then C-star algebras probably wouldn't be a thing, because you could always just study the space x instead. Okay. And sometimes people talk about C-star algebras and they say it's like a non-commutative topology. And what they mean by that is that when the C-star algebra commutes, you're really studying x. And by studying x, I mean studying the topology on x. So when things don't commute and you study the C-star algebras, the idea is that it's kind of like you're studying the topology of some non-existent thing. Just kind of weird. People in this field have a tendency to think like that. It's very strange in my opinion, but okay. And then finally, another example of a C-star algebra is the n by n matrices, but you make them complex valued. So the entries have to be complex numbers in general. If H is finite dimensional, then this is B of H. But it's a lot more concrete in a lot of cases than B of H. So if you want to multiply the things in the C-star algebra, you multiply the matrices. You want to add them, you add the matrices. Addition is entry-wise. Take adjoints. Well, what you do is you take the transpose, and then you take the complex conjugate of each entry, and that's the adjoint of a matrix. So that's another very concrete situation for C-star algebras. Now, one other thing. Wait, I don't know if I... no, wait. Maybe I didn't add a slide on this, but... wait, did I put it... Oh, I put it back here. I skipped a slide. Okay. That's fine. Maybe this slide should have come before that one anyways. Right, so not only is B of H a C-star algebra, but you can take some subcollection of B of H and then add in all the products and sums you can get by combining all the elements together, and then take the closure, and you always get a C-star algebra that way. So this symbol means that everything in A belongs to the thing on the right, B of H. And if you have such a collection of operators where you can add them and multiply them together and scale them and take adjoints, etc., and stay within that collection, and this technical condition that it's a closed subset, then you have a C-star algebra. And actually, such collections of operators inside the bounded operators of Hilbert spaces, in a certain technical sense, these are all possible C-star algebras. So if you were to write that formally, you would say that for every C-star algebra A, there's some Hilbert space out there, H, and a faithful representation from A to the bounded operators of H. And then phi preserves all of the algebraic and analytic structure of the C-star algebra. So you can study A by studying its image in here. So you can this is telling you that instead of studying A, if you wanted to, you could study bounded operators on some Hilbert space. I guess I
have a question.
Yeah.
Can you explain the difference between closed and topologically closed?
They're the same thing. I'm just being...
Wait. Well, it says as well as, right? Doesn't that imply it's different?
Oh, yeah, this closed. Yeah, good catch.
Yeah.
So I'm saying closed under the operations in the previous slide, which means that when you do these operations, you stay in A, right? So if you have some collection for which when you do all those operations, you can't get outside of A, I'm calling that collection closed under the operations, under those operations. That's what that means.
Okay. Like, and what's topologically closed?
It just means that you need to be able to take limits. So when you take limits of things in A, you stay in A.
Okay.
Like, if for calc, like in Calc 2, when you take limits of sequences, right? It's exactly like that. You take all the sequences in A.
Yeah.
They either have a limit or don't have a limit. But if they have a limit, it's also required to be in A.
Okay.
Yeah. So this
kinda.
yeah, it doesn't matter much, that part at least. I should explain this notation here. So basically it's saying that phi, the type of phi is a function. The arrow is like means function. And phi is a function which takes things inside of A and outputs things in B of H. That's what phi is. Representation is something much stronger, but I'm not going to get into it. So then I guess a question you could ask is, why even study C-star algebras at all? Why not just start studying Hilbert spaces? But the operators, most mathematicians are more interested in the operators than the vectors. Because linear algebra is actually very simple, abstractly, in some ways. So operators now are the more interesting thing to study. How operators aren't necessarily seen as just things that take vectors and give you vectors. They're seen as things that interact with other operators. So you study the operators and their interactions with each other instead of just the vectors. And then really, so C-star algebras don't care about the Hilbert space, which ends up being a really powerful thing, because you could have multiple different Hilbert spaces and multiple different operators which give you C-star algebras which really are the same or isomorphic. And so by studying the C-star algebra, you can study all those situations at the same time. Okay. Now, the other really cool thing that you can do with C-star algebras is represent things which you would expect to only be able to understand in the Hilbert space picture, but you can represent those algebraically. So for example, if you have an operator S on your Hilbert space H, it can be special, right? And here are 4 ways in which it can be special. It can be an isometry, unitary, a projection, or a partial isometry. So what is an isometry? Well, an isometry, for example, is an operator which doesn't change the length of its input. So when you take the length of the output of S, so you take X, plug it into S, take the length, it's the same. You get the same thing as if you just took the length of X. And that's true for every vector in your Hilbert space. But you can represent this, in fact, algebraically. You can say that when you take the adjoint of S and multiply by S, you get the identity operator. These are equivalent. notice that the thing on the right involves norms. So usually if something like this involves norms, you'd say it's an analytic characterization. So if I say that, that's what I mean by analytic. But the thing on the left is algebraic. It only involves this algebraic identity S star S is equal to 1. And this isn't necessarily expected, that you're able to translate analytic things into algebraic things and vice versa. Here's another example. If you have a surjective isometry, so what does surjective means? It means that every vector is the output of your operator, is some output of the operator. So it's like if you had a function on a number line whose values which takes on values between 0 and 1, it wouldn't be surjective because it doesn't take the value 2 ever, for example. But you could have a function where every number is the output of the function at some point, and that would be surjective. Well, we can talk about when an operator is surjective. So when every vector is an output of the operator. And a unitary operator is very important. It's an isometry which is surjective, and you can characterize this with this algebraic identity, where you also require S times S star to be 1. The analytic, maybe the more useful analytic characterization is that unitary operators don't change the inner product at all. Okay. You also have things called projections, and it would be, I was trying to think of a good way of like succinctly writing the analytic definition of this without needing to explain a bunch of things, but I can't really. So just think of like a projection as something that smushes your Hilbert space, and you can represent projection as some operator S for which it's equal to its adjoint and its square. And then there's a type of operator which generalizes all three of these things called a partial isometry. And these are things where you take this product S times S star times S and you get back S. So all three of these things are partial isometries. And you can check that pretty easily. For example, for an isometry, you can multiply both sides on the left by S, and you get that S times S star times S is equal to S. Partial isometries are particularly nice operators. Think of them as like operators which are isometries on part of your Hilbert space and 0 on the other part of the Hilbert space. I'm intending to be pretty vague with that, so don't worry if it doesn't make too much sense. But so because we can characterize these operators algebraically on a Hilbert space, then when you look in the C-star algebra, you can write down all of these things still inside of the C-star algebra. And what this allows you to do is it allows you to say when you have a projection in a C-star algebra, and even though the C-star algebra doesn't have a Hilbert space attached to it, if you, for example, in the previous slide, if you take a representation of the algebra, whatever that means, basically it's just saying that, you know, you're finding operators which represent the elements of your C-star algebra in a natural way. If you take a representation of a projection in the C-star algebra, you'll get a projection on the Hilbert space. So it's kind of a really, it shouldn't be expected at all that you can represent these things algebraically, but you can, and it's one of the things that makes C-star algebras so useful. Okay, so that's the introduction to C-star algebras. So if you have questions again, you can ask now. Otherwise, I'm going to move on to graphs. I'll have to now tell you what graphs and stuff are.
I like graphs. Let's see them.
Okay, so what is a graph, right?
Oh shit! Never mind.
It's you forget about your algebra class where you're like taking graphs of functions. What mathematicians call a graph, I mean, actually, sometimes they do call a graph that, but more mathematicians call graphs these things. So, actually, this is in my field, people just call these graphs, but in other fields, people would call these directed graphs. But it doesn't matter for here. I'll just call it a graph. Question?
Well, what exactly is your field? Because sometimes you say mathematicians, and then sometimes you say physicists.
Yeah, my field is operator algebras. Here, boom, operator algebras. See?
Okay.
In this intersection between
Okay.
algebra and analysis. And there's some nice physics that you can use, but, operator algebras. Okay.
So, but you keep saying physicists and mathematicians, but I have not heard you reference what the analysts think.
Analysts are mathematicians. They're mathematicians. So this is a name for a field of math.
Is physics a field of math?
There's mathematical physics, yeah. But then there's just physics. I'm referring to mathematical physics, I guess.
Everything is math.
Yeah, you probably should have clarified that.
Okay. Yeah, my bad.
I'm kidding. Okay, bye. I mean, not bye. Keep going.
Yeah. Okay, what is a graph? Because I haven't told you what a graph is. All I've told you what is what it's not. So, a graph is a collection of vertices and edges. That's literally it. Now, in order to talk about edges, edges go between vertices, right? If you have a graph E, you label the vertices as E superscript 0, and you label the edges as E superscript 1. And then you need to be able to talk about what vertex an edge starts at and what vertex it points towards. And that's what R and S tell you. So R is a function. It takes an edge and gives you a vertex, and basically it tells you what vertex that the edge points to. S is a function which gives you an edge and also gives you a vertex, and it tells you what vertex the edge originates from. So I have an example of a graph here. So here we have 4 edges. So the E0, the first edge, goes from V0 to V0. So if you were to take the source of E0 here, you'd get V0. And if you were to take the range of E0, you'd also get V0. But you also have these edges E1, E2, E3. For example, a source of V0, S of E1 is V0, and R of E1 is V1, etc. And if you want to think about these collections E0 and E1 in terms of this example, you'd say E0 is equal to, and then these braces just mean set or collection. The order here doesn't matter. I could write these in whatever order I want, but the vertices are just the collection here of 3 things, V0, V1, V2. And the edges, the edge set is the set E0, E1, E2, E3. And then I've written some of how you would define R and S. In particular, I've only written the things whose output is V0, but for example, the range of E2 would be V2, so you still have to define those when you're defining a graph, of course, but I just, yeah. Abigail
That wasn't that bad.
left.
No, I'm still here. My phone died, so I came to watch on LinkedIn.
Okay, good, cool. Yeah, any questions?
I like graphs again.
Okay, good. Yeah, graphs are pretty cool. If you have questions about how graphs are defined, this is definitely the time to ask. Okay. Now, graph C-star algebras. Basically, people like C-star algebras, but C-star algebras are really, really complicated, and people are not so good at imagining these extremely abstract things. Like, it's not something you're just born with. Like, almost like people pick up a number sense pretty easily, but it's really hard to get a C-star algebra sense, right? So what ended up getting invented is a way of taking a graph, which is a thing that's pretty intuitive. It's like something which, physically there's a lot of context for. Taking a graph and creating a C-star algebra out of it, which in this process always works, which is pretty cool. And they did it in a way where some properties of the graph correspond to properties of the C-star algebra. So not every property of the graph is going to correspond to something directly about the C-star algebra, because there are lots of different graphs which can give you the same C-star algebra. But some properties of the graph correspond directly to some properties of the C-star algebra. And that's a very valuable thing to have. It allows you to study and come up with examples of C-star algebras without having to, just by using graphs, which are much more intuitive. So how are these things defined? Well, what you do is you basically start throwing, and really there's a very nice more abstract way of thinking about this, but I think it would be more confusing. So I'm going to describe like the very concrete way you would do this. Basically, you require your algebra to have some things, and you take all possible products and sums of these things and stars, and you then create that way a C-star algebra. But when you're computing these products and sums, they're required to respect these relations. So let me describe this. So for each edge, you have a partial isometry, and for each vertex, you have a projection. Then these projections are required to satisfy the following identity: PV/PW is equal to 0 whenever V and W are different vertices. And actually this is an algebraic relation, but just like how I was showing you how you can define projections and partial isometries algebraically, this relationship has a very geometric meaning when you go into Hilbert spaces. What it means is that V and W correspond to sets, or like you could call them subspaces in your Hilbert space, which are orthogonal. Orthogonal, if you took Calc 3, maybe you remember that word. It means the vectors are pointing in different directions, and not just different directions, but in as different directions as they could be. And that's exactly what it means here. So then you require this relation, S of V star. S of V is projection onto the source of E for every edge. So source of E is a vertex, remember. So we can take the projection for that vertex, and we're saying that that's equal to whatever this element is. And again, this has a very geometric interpretation. S of E is a partial isometry, and I told you guys sort of what it means to be a partial isometry. It means you're an isometry on some subspace, and then you're 0 on the complement, or really the other stuff. Maybe you can think of it like that. Well, the thing you're an isometry on, that's represented by...
Could you review the isometry concept one more time briefly?
I can't hear you, Abigail.
Oh, could you review the isometry concept one more time briefly?
Yes, in isometry...
Just isometry basic, yeah.
In isometry, it doesn't change the length of its vector, of its input. So when you take the length of the output, it's the same as the length of the input you gave it. It's an operator which does that. In
Okay,
a
thanks.
C-star algebra, there's an algebraic characterization. So, but my point is that these relations actually mean something geometric when you think about things in a Hilbert space, which I think is cool. So you can really think about these things very concretely if you wish. And all I was going to say is that this thing SE star SE, that represents you have the partial isometry SE, and this thing on the left represents the space on which the partial isometry is a actual isometry. So the thing on which it's not zero. Okay, and then this final relation is a bit more mysterious. Basically, if you have finitely many edges, and at least one edge whose range is V, so I don't need to really explain all of this notation because it won't appear again, but that's what this means. So if you have some vertex with an edge pointing into it and only finitely many edges pointing into it, and you take, and you take, for each edge whose range is V, you take this element of your C-star algebra, and then this symbol means you add all of those up together. So you add them for all the edges whose range is V. You have to get this projection for V. This condition is more mysterious. I don't have much I could say about it, really, but it just what ends up making the study of these algebras interesting. If you remove this, then your algebra is a little bit too big. So you require this, and all of a sudden you get sort of a good, at least from all the research people have done, you get something good, right? So you require this other relation, and like I said, you just throw all these partial isometries and projections in some bucket, and you start mixing them together, multiplying them together while using these relations, and you get everything in the C-star algebra. Or maybe if I want to be more precise, I can say that you can approximate everything you get in the C-star algebra that way. So, yeah. Here's an example of a graph C-star algebra. Think of a graph which has one vertex and one edge. There's a projection for this vertex, piece of V, if this vertex was V, but I haven't labeled it. Because there's only one projection, it turns out that this piece of V is the identity, the unit in the C-star algebra, which I'm labeling a 1 because it's labeled 1 because when you multiply something by 1, you get the same operator. So, okay, so the projection for this vertex is V, for V is 1. So this relation tells you that SE star SE is 1, and this relation, since there's only one edge going into V, this relation tells you SE SE star is also equal to 1. So that's where this relation comes in. So you want to get the C star.
I have a question.
Yeah. Yes.
All right. Are we supposed to know that the projection is 1, or are we just trusting?
Just trust me on that one. Yeah.
All right,
it's not hard to see if you were to actually. I mean, like, for someone with a little of experience in computing things inside of C-star algebras, it's not hard to see that it needs to be 1. It's 1. Okay.
Gotcha.
So what you end up with is a C-star algebra where you have this thing S sub E satisfying this relation. This tells you that S sub E is a unitary. If you're, I wouldn't expect you to remember that, but that's what that slide said. And you want the C-star algebra for this graph. Well, you just take S sub E and you take all possible products and sums of things, and you, whenever you have an S sub E star and an S sub E next to each other, you replace it with a 1, and then you have to take topologically the closure or whatever, but not super important. What do you get? You get something which structurally is isomorphic to the continuous functions on the unit circle. This T is the unit circle. So maybe this is a bit mysterious. I can tell you how you can, and explicitly how these things are the same actually. So, but this might be confusing since I haven't written anything down. Take all complex numbers and then take only the complex numbers whose length or absolute value is 1, and you get a circle. That's this T here, this boldface T. And then this S sub E corresponds to the identity function on that circle. So the function which takes points on that unit circle in the complex number and returns itself. And once you identify S sub E with that function, you get that these are the same algebra. Here's something you could do. You can just add an edge. So now we have 2 edges, E and F, and still 1 vertex. And this is by definition called the Kuntz algebra on 2 generators. So it's 2 isometries. It's the C-star algebra generated by 2 isometries, and it was when people before graph C-star algebras were a thing. It was the first example anybody ever came up with of a simple, separable, and purely infinite C-star algebra. And I'm not going to define those things, but people at the time cared about whether such a thing existed. And this is the actual construction. The construction of this specific algebra is what inspired people to generalize, particularly Kuntz and Krieger, to generalize things to arbitrary directed graphs. And yeah, so when you take this special graph, you get this historically important C-star algebra. Okay, now I've been talking about things in terms of edges and vertices, but in my opinion, and for the project that I'll be talking about, it's not actually the correct way of thinking about things. Instead, I'd like to think about all paths in my graph. So if you have a graph and you have some collection of edges, now the order matters. So I've labeled them E0, E1, up to En. Then I'll say a path is such a collection of edges, E0 through En, such that the source of some edge EJ is the range of the previous one, EJ minus 1. What is this saying? Well, it's saying that, for example, I could have E1 then E2 because the source of E2, which is V1, is the same as the range of E1, which means I can follow E1 and then follow E2. But if I did E0 and E2, I can't put those 2 edges together to get a path of length 2. So that wouldn't form a path. Then when you have such a collection of edges, you can write the path, at least, we write the path as a product of the edges. And really this is just notation. This is notation for the path which starts at E0 and ends at En. Notice that this composition, if you're following from the start of the path to the end, isn't from left to right like you might expect. It's actually from right to left. And the reason why it's that way, if maybe you can imagine, is because of function composition. That's the order in which function composition happens. So that's the order in which we write our edges. To be clear, E0 through En are not elements of a C-star algebra. They're just edges, and we just write a path by writing these edges next to each other and requiring that the source of the next is the range of the previous. Then once we have paths, we can define the source of a path. So the source of f is the source of E0, the source of the first edge. And the range of f is the range of En, so the range of the last edge. Then whenever f and g are paths, for which the source of f is the range of g, you can actually concatenate f and g the same way you would concatenate two edges, and you'd get a new path, fg, where you first follow g and then follow f. And for example, the source of fg would just be the source of g, and the range of fg would be the range of f. Then, if you have a path f in your C-star algebra, say it's equal to this product En through E0 of edges, you can define, and you're not creating a new element in your C-star algebra, you're labeling elements that already exist. So you can create a label for the special product of these partial isometries in your C-star algebra. So you take the partial isometries for the Ens through E0s, you multiply them together, and we'll call that the partial isometry for f, because it turns out when you multiply partial isometries, you get partial isometries still. And now, if you study graph algebras a bit, then you would find a good reason why we require that this list of edges is actually path, that the source of the edge is the range of the previous. And it's because if that weren't the case, then this product of partial isometries would actually be 0. And that's enforced by the relations which define the graph C-star algebra. So really, then, you can, instead of thinking of these special partial isometries for edges and these special projections for vertices, you might as well just think of all of the partial isometries for all the paths. And then if you have a path of length 0, formally what that means is just a vertex. So even these projections for a vertex are of the form SF for a path f of length 0. Any questions about that? Okay. Now I can finally sort of vaguely, but I can vaguely introduce what my idea is in one of the current research projects I'm working on this summer, and what I hope will be my thesis. And then I'm going to spend the rest of the talk like actually trying to make it a little bit more concrete in your minds. When you're studying graph algebras, sort of by the stuff in this previous slide and by some other nice things that happen in the C-star algebra, it's actually more natural to think of having a partial isometry for every path than just for the edges and vertices. It turns out you can actually define, and in fact it's really natural to define graphs just in terms of their paths. The intuition for this is that every path in a graph is a finite product of edges, right? Because if you have a path of length n, then you can chop it up into n pieces, each which have length 1, and then those are the edges. So when you're drawing a graph, you only need to draw the edges, right? Because once you have the edges, you know all the possible ways of combining them to get all the paths. So here's another really cool way of thinking about a graph. You can define it by saying a graph is a small category, and I guess it's somewhat important for me to tell you what that means here. So think of a category as so this algebraic object where you can multiply things together, where you can multiply some of the things together and get new things. And really, categories are supposed to represent function composition usually in a way. So a graph is a small category and a functor. So functor is just a fancy word for a function from a category into another category, really. So this functor, I'll call it the length functor. It's a function d from your category into this bold-faced n. This is the natural numbers. So natural numbers are the whole numbers. These are non-negative integers. So the integers which are at least as big as 0. This function represents taking the length of paths. So the small category is the collection of paths on your graph. And then the whole number you get from, or the natural number I'll call it, you get from taking this function evaluated at the path, that's the length of the path. And so anytime you have a category and this function which satisfies the property below, you actually get a graph. It's the same thing as a graph. So what is the property below? It says that for every path and every number which is less than or equal to the length of the path, we can find unique paths, f and g, such that E is the composition of the paths f and g, and the length of f is n. So basically you can take the path E, you can take the last n edges of your path E, chop it in half there, and those are your f and g, and those are the unique f and g, which will give you the path E. So this definition of graph actually gives you the same thing as the definition of graph I gave you before. And it's a very natural way of thinking about graphs, especially in this context where for C-star algebras, the paths are what matter. So now basically the idea for my research is to change this boldface n. My advisor actually in like, I think it was 2000, 24 years ago, he took n and replaced it with k copies of n. So now you would have this function from your category into k copies of the n. So basically, instead of the length being one number, it'd be k numbers, and you'd still have the exact same factorization property. You no longer get things which are just graphs. You get things called k graphs, and you can still make C-star algebras. And he basically wrote a paper with another mathematician where they show that these C-star algebras, you can still prove things about these C-star algebras from the k graphs. And now my idea, and I'm intending to elaborate a lot on this, is to allow the paths to have infinite length. So that would mean replacing this n with something where the all of a sudden, if you think of d as the length, then the length is allowed to be infinite. And this is kind of a technical thing, so I'm going to give you a precise description of what I mean now. Are there any questions before I move on to the next section? We're gonna make a complete change in context here. So my job now is to explain what I mean by infinite paths, and elements of the natural numbers, so integers which are at least as big as 0, can be thought about in two main ways. And it turns out that these two ways actually give you two different ways of generalizing them. So one way of thinking about the natural numbers is as a quantity. So if you have a set, a collection of things, and it's a finite collection of things, you can count the number of things in that collection, and you could call that the size of that collection. But then you can have infinite collections of things, right? You can think about all integers instead of just some finite collection of integers. And if you generalize the natural numbers, if you think of the natural numbers as telling you how big something is and generalize that, then you get something called cardinality. And that's like ubiquitous in math. When someone says something is infinite, then that's usually what people mean. They're talking about how many things are there. But the thing I mean is actually something different. And the way you get this different thing is by thinking of the natural numbers instead of as specifying how many things there are. Instead, you think of as specifying, there are two equivalent ways of thinking about it, either as specifying where something is or specifying how things are ordered. But I think maybe it's more intuitive to think of it as specifying where things are. But when you generalize this, you get something called ordinals. And it's called ordinals because it's really generalizing how you order things. So for example, you can think of the number 5 as telling you as say all of the natural numbers less than 5, and these have an order structure. And you can think of, here, let me just describe more, and then hopefully this will make a little bit of sense. So right, like I said, ordinals generalize ways of ordering things. But there are lots of ways of ordering things, and maybe there are too many ways of ordering things to get a good number system if you just consider all ways of ordering things. I'm thinking of particularly well-ordered sets. So we say something is well-ordered, and remember, this symbol just means that F is a collection, and everything inside of F belongs to the thing on the right. So everything in F is a whole number, some integer which is at least 0. And the natural numbers are well-ordered because no matter what collection of natural numbers you have, if it's non-empty, it has a least thing as a least element, something that is smaller than all the other elements. That's what it means to be well-ordered. That is the definition of well-ordered. And this second part is a bit technical. So if you have a question about it, please ask, but I sort of expect it not to make sense too. So, but whenever you have something that is well-ordered, you actually get sort of a strategy or a machine for proving something about that collection. In particular, if you have some property P, I'm just labeling some property that you might be trying to prove about some collection. If you have some property P, say of whole numbers, P could be the number is even, for example, right? If you have some property P and say this property is special in that whenever P is true for all the things less than N, then it's also true for all the things less than M, then it's also true for M. So if P has this special property that whenever it's true for all the things less than M, then it's also true for M, then because the natural numbers in this case are well ordered, this automatically implies that P is true for all natural numbers. Because if there was some number M for which P wasn't true, you could choose the least such M, and then since it's the least M for which it's not true, P is true for all things less than M, and this would contradict the fact that P has this special property here given by the first bullet. And so what I'm trying to show you is that we didn't use anything about arithmetic on n. We only used the fact that n is well ordered to have this special property. And so there are lots of other well ordered sets, and that strategy for proving that some property of a collection holds will work on any well ordered set. So that's why well ordered sets are important. This strategy is called induction, and induction works on the well-ordered things. Okay, if you have a question about this, you're allowed to ask. Please do. Otherwise, I'll just continue.
Yeah, Ben, I had a question on the last slide. Oh, this slide, yeah. Are you aware? It looks like it says men.
Of what?
And within
It just says men.
there's an element.
It's quite an observation.
Thank you. That's
Wait.
all.
Wait, what?
So
The
M
third
is
to
a
last
set of
line.
n.
EM is
Yeah.
not true for some men. It's true for all men.
That's what I'm saying. Yes, stupid
Strange
gets it.
observation. Well, yeah.
Oh, wait, there's a typo.
No,
What?
it's not.
No,
Wait.
no. It's that, Ben, I think it doesn't come across this way to you because to you those are very clearly mathematical symbols. But to the math noobs, that just says men.
Oh, yeah. I see what you mean now. Okay, thanks.
He's
The
like,
math
wait.
Oh, yeah,
phrase,
Where did
great
I type that? I
feedback.
said, oops. Yeah.
Yeah, you're welcome.
Thanks.
Wait, that's not the
Amazing.
typo, right?
No,
There
it's
was
not a
He,
typo.
he just got scared because he thought it said men somewhere.
Oh.
No, I wasn't scared.
Oh.
I would be surprised if there weren't typos, honestly. I'm not
doesn't get
scared.
scared.
I gave my talk in the conference, and we were like going over it the night before, like at like 11 o'clock, like super tired.
Oh.
And it wasn't this talk, but there were like typos, and I told myself I was going to change them, and then I just never changed them. So when I gave my talk, there were lots of typos. So,
No,
but
that's
Makes
just
you
the
look like
you know,
official.
Yeah.
yeah,
Like,
just,
what are you gonna do? Call this out? Raise your
Right,
hand
like-
You get away with that because you're in the obscure field of
dude, people make typos all the time.
operational
Operator algebras. People make
Operator
typos all the
algebras.
time. It does not. Literally
But
every
do you think
single
most
talk
of
at
your
that conference
audience-
had typos.
Do you
You're
think
not an
most of
English
your
major,
audience would
so-
recognize the typos, or do you think they would assume that they're missing something?
Well, I was like literally like looking at my slide, and I pointed the typo out myself. So at that point, they probably did, but it was
I
kind of an
see.
important
I see.
typo too. So I kind of had to call it out. Oh, so yeah. Back to ordinals, right? I'm glad that this made sense. I wasn't sure if I could properly
It
describe what
didn't
was
seem too
happening.
bad.
What was happening here?
Yeah.
That's good. Okay. Yeah, and really, like, this is what makes ordinals what I'm about to define ordinals, and this is what makes ordinals cool. The fact that these are the things in which you have induction, pretty much, at least like totally ordered induction. So I've told you that there are lots of well-ordered sets. I haven't given you any examples other than the natural numbers, right? You can take any finite, take the numbers from 0 to n for some finite n, that's still well-ordered because it's just a subcollection of the natural numbers. So that's an example of a finite well-ordered set. N, the natural numbers, is an infinite well-ordered set. Now, just define some new object. It doesn't matter what it is. You just, because we're just thinking abstractly, right? Call it infinity. Now, I'm only calling it infinity suggestively, but infinity isn't supposed to mean anything. It's just a symbol here. Then we'll make a new well-ordered set by adding in this symbol infinity and saying that for every natural number n is less than infinity. And then we take n along with That's what this symbol means. Combine these two collections. We say n along with this infinity, and we get a well-ordered set still. Meaning if you take any subset or subcollection of this set, it's still if it's non-empty, it has a least element. So by definition, still well-ordered. Now, if you have two well-ordered sets, sometimes it's possible to relabel the objects in one set to something else, and then it becomes clear that they're the same. So for example, you could have the numbers 1, 2, 3, and then 4, 5, 6. So you have two collections. Both of them have three things. And actually, you can sort of intuitively see that the order structure between these two collections is the same, even though the sets don't have the same things in them. The way you do that is by relabeling one. So replace the 1 with a 4, replace the 2 with a 5, replace the 3 with a 6. We haven't changed the order of anything by doing this process, and we've gone from the first set to the second set. So because of that, this tells you that the first set and the second set are really the same in terms of being ordered. We call that order isomorphic. So formally, if you have two well-ordered sets, A and B, you say they're order isomorphic if you have some function phi from A to B. It has to be bijective. What does this mean? Well, it means that phi reaches every element in A, and every element in A gets sent to something different. Really, this is mathematically what this is, or like intuitively, you're relabeling the things in A to things with things in B. So you're taking every element in A and assigning it a unique thing in B, such that you reach everything in B. Okay, so two sets A and B are order isomorphic if there's this function, which is a bijection, which satisfies this special property that whenever you take two things in A, call them A and B, if A was less than B, then phi of A is still less than phi of B. This is telling you that phi has to preserve the order structure. So you can't just rename things however you like. You have to rename them such that if two things compared one way before, they still compare the same way after the renaming. Now, an ordinal, formally, is an order isomorphism class of well-ordered sets. What does this mean? Well, basically, you think of all well-ordered things. So all collections of things in math which are well-ordered, all sets which are well-ordered, and then lump together the ones that are order isomorphic. So if A and B are order isomorphic, consider them the same ordinal, because they belong to the same, by definition, order isomorphism class. See, the order isomorphism class is the collection of things which are all have the same well-ordered structure. They're all order isomorphic. So you take all these classes of things which are ordered the same and they're well-ordered, and all of those together are the ordinals, and any one of those classes of things is an ordinal. So, for example, we could take the natural numbers. We can say, consider all sets which are order isomorphic to the natural numbers. Those also have to be well ordered, by the way. Take the collection of all such sets and call that omega. So now omega doesn't care about how you label the things. It only cares about the structure of the things, how they're ordered. And since omega is the order isomorphism class of the natural numbers, what this means is that omega is really representing all things which are ordered like the natural numbers. Then one cool thing you can do is define for example, and there's lots of other arithmetic you can do with ordinals too, by the way, but one cool thing you can do is define the sum of two ordinals. So if you have two well-ordered sets, you can take the order isomorphism class, which I'm writing with these brackets, and these are both ordinals. So the bracket A and bracket B, these are both ordinals. And you can actually define the sum of these two ordinals to be, by definition, the class of this thing. So now I have to tell you what A and then this square cup thing B means. It means what it means is you at least with respect to the order, what it means is you take the things in A, then you take the things in B, you put all the things in B above the things in A, and otherwise keep the structure of ordering the same. So formally, you would formally A with this square cut B is the combination of A and B, where now these are required to be disjoint, meaning that there's nothing in both. You combine them together and you define the relation, the order, less than or equal to, so that everything in A is less than everything in B. And that is bracket A plus bracket B.
I have a question.
Yeah, question, yes.
Okay, so you said, I'm sorry if you said this, but an ordinal is not necessarily what the brackets mean, right? Brackets could mean just like a list of things, right?
Bracket means class. So the
class.
Yes. So
okay.
Really equivalence class, but here isomorphism class. But the notation is ambiguous. I'm like sort of just saying in my talk I'm using the bracket to mean that, right?
Oh, okay, gotcha.
Yeah, but if you see brackets
I was
elsewhere,
thinking otherwise you could just like not have the brackets for like where you have what is it? I know it's not W equals N. I forget the Greek now. But yeah. You could just not have those brackets there, right? Otherwise.
Yeah, but then my definition wouldn't be agnostic to different ways of labeling things. So using the brackets,
gotcha.
I'm considering all things which are labeled the same, independently of the label, instead only caring about the order. Yeah, that's sort of like a really powerful thing in math that you can do with in general. But yeah. Okay, so so we can define the sum of ordinals, and we've actually already seen one example of the sum of two ordinals. So if you take omega, right? Omega is the class of natural number, the order isomorphism class for the natural numbers. And then 1 is an ordinal. What does 1 represent? Well, it's the collection with only one thing. So there's only one way to order a collection with one thing. And the order isomorphism class of that is what we call the ordinal 1. So then you can add those two together. So what you're doing is you're starting with the natural numbers, and then you have this set B, which is just the set containing infinity, this symbol at least for infinity. And you're defining this new collection such that everything in the natural numbers is less than infinity. And then the order isomorphism class of that is, by this definition, omega plus 1, and that agrees with what I was describing on the previous slide. Now here...
Should that be a square bracket then?
Here?
No, that's like a square U instead of a...
Oh, it can be, but here I'm just basically assuming that you understand that this symbol, infinity, is just some formal symbol we've defined, so it doesn't belong to the naturals. I could have written square bracket. It wouldn't have been wrong, but
I see.
the square bracket just means you're just telling there's actually two different conventions, but maybe the one I just like to write it when I'd like to tell the person who's looking at the math that these two things are disjoint and I'm combining them together. Here I didn't write it because I figured it, it's understood that this
It should
infinity
always
symbol
be
doesn't
less than,
belong.
so yeah.
Doesn't belong to.
Yeah.
Yeah. One very, very interesting thing, and actually key to my research that I'm doing, this project at least, is that addition does not commute. Ordinal addition does not commute. Alpha plus beta, if alpha and beta are ordinals, is not the same thing as beta plus alpha. And you can think about this. So suppose instead of having omega plus 1, I had 1 plus omega. So maybe I can, instead of having the symbol infinity, because infinity was supposed to be suggestive, maybe have the symbol -1 instead. Then instead of adding a new thing after all the numbers, I'd add it before all the natural numbers. So remember, these are integers which are at least 0. If I put a -1 in front of that, so if I write out the 0, 1, 2, 3, etc. on a number line and write a -1 in front of that, then I can shift everything over to the right and I get basically a copy of the natural numbers. So omega plus 1 is different than omega. Omega plus 1 does not equal omega because it contains something bigger than all the other things. But 1 plus omega is equal to omega. So you can already see that alpha plus beta is not equal to beta plus alpha. And even stranger, you can take 1 plus something and get the same thing. And actually, usually for most ordinals, that happens even. So very strange and unintuitive these ordinals can be. But it's pretty cool. So there's this really cool picture you can find on Wikipedia if you want to seriously think about ordinals, because they are really trippy so you can think about going around on this spiral, right? You start at 0. 0 is the ordinal, which represents having nothing, a set containing nothing, right? Such a set is automatically well ordered, and it's perfectly fine, perfectly admissible under our definition for ordinals. So you can move counterclockwise around this spiral, and you get increasing ordinals. So to go from one tick mark to next, you add 1. So 0 plus 1 is 1. 1 plus 2 is 2, etc. You do this for all the finite ordinals, you get exactly the natural numbers. So everything is exactly how you'd expect. Nothing really new going on. Then eventually you get all the natural numbers, right? So you approach this line, but you never touch it. And you want to add something bigger than everything else, kind of like adding infinity, how we added infinity to the natural numbers and said everything was less than it, and we got a new ordinal. Because you can only add 1 for so long and only get so many ordinals, you have to eventually do something like that to get the next ordinal. So what you do is you take all these finite ordinals and then add something that's bigger than them all. So you get the first so-called limit ordinal, omega. Now, you might think, oh, omega and all of these other things looks like omega plus 1, but omega represents the things less than it. So if you look at this picture and you're looking at omega, you can look at all the ordinals less than omega, and then that is the order isomorphism class of omega. That's another really cool thing about ordinals. The ordinal is sort of represented by all things less than it. Okay, and then omega plus, we can add 1 to the ordinal to get omega plus 1. We can add another one to get omega plus 2, omega plus 3. This corresponds to adding one extra element beyond all of the finite ordinals, then 2, then 3, then 4. And we keep doing that, and we get 2 copies of the natural numbers. And that is the ordinal omega times 2. So basically you take, or you can also write it as omega plus omega, right? You take one copy of omega, the natural numbers, and then you slap another copy of omega on the end of it to get another copy of the natural numbers. And you can repeat that process to get omega times 3, omega times 4, omega times 5. You keep doing that, and eventually you're only going to approach this next ordinal omega squared. So what you want to do then is add an ordinal which is bigger than all of those, and that is omega squared. And you repeat this process, and you get omega squared plus omega squared plus omega times 2, and then you get omega cubed, omega to the 4th, omega to the 5th. And eventually you only get closer and closer to omega to the omega. And to get to omega to the omega, you need to take another thing which is bigger than the rest. And that's how you get this picture. It's quite a trip, but I think it's really, really helpful for understanding ordinals. What was your question?
Is there a reason the triangles start at omega squared?
Oh, basically this is showing that after this point, like if you were to, so notice that going one circle around, I go to omega, right?
Yeah.
But I don't go to 2 times omega by going another circle around. I instead go to omega squared.
I see.
So at this point, you can't continue drawing the picture like this if you keep drawing the lines. So this is just like showing you that, yeah, the lines are there, but basically they're just really dense at this point, right? So
okay.
Yeah.
Very trippy.
Yeah, it's really, really crazy. By the way, omega to the omega, you might think that like that's a really big ordinal or whatever. Actually, if you think about it in sets in terms of size, all of the ordinals on this picture, if you look at the order isomorphism classes, they all have the same size. They all have the same cardinality. So
yeah,
this is bigger in a different sense, really. And you can write ordinals that are much, much bigger than omega to the omega. And then you can even think about the first ordinal, which is bigger than all the countable. You can think about the size of these ordinals in terms of cardinality, and then there's like some first ordinal which is bigger than all ordinals which have the same cardinality as this, and it's really trippy. People study this. People who do set theory study these things. Which is kind of interesting. But my job isn't to study them. My job is to use them, because I think not a lot of mathematicians really use ordinals, but I've found a really good use. So finally we get back to, what did I mean by having paths of infinite length? I meant the length of the paths is these ordinals. Okay? So my definition of an ordinal graph, so it's a generalization of a directed graph, or a graph. Directed graph is the same thing as graph, right? It's a generalization of a graph where the paths are allowed to have lengths which are ordinals. So in particular, if you have a pair lambda, this is capital lambda, by the way. If you have a pair lambda and d, then it's an ordinal graph if lambda is a small category. And again, just think of category. This is like the collection of paths. We can combine 2 paths together if their source and range match. And small just basically is like a technicality you need to actually be able to make a C-star algebra, but it's kind of misleading because these things are can be as big as you can imagine, really. Okay, so lambda is a small category and d from lambda. And now, before we had natural numbers, here we have ordinals. D from lambda into ordinals is a functor with the exact same factorization property as before. So for every path in lambda and every alpha and every ordinal now, alpha, which is less than the length of E, there's unique paths F and G such that E is F composed with G. So in other words, E is what you get when you can split E into F and G, and the length of F is alpha. So alpha doesn't have to be finite. Alpha can be any arbitrary ordinal, and the length of E can be any arbitrary ordinal. So now something really interesting for ordinal graphs happens. So if you have paths and you have, say, E, F, and G, and you have this algebraic relation between the paths, so composing E with F gets to do the same thing as composing E with G, then it's very easy to prove using this definition, this factorization property, that you can cancel the E's and you get F is equal to G. The path F is equal to the path G. We call this left cancellation. So ordinal graphs are left cancellative. But, and this is unlike graphs and unlike K-graphs, ordinal graphs are not right cancellative. So there are plenty of examples, in fact, most interesting examples you can find, where you have paths E, F, and G such that FE is equal to GE, but F does not equal to G. And this is really counterintuitive in general. When I was describing this idea to my advisor at the conference, he was getting we were working with things in the C-star algebra because I was defining everything formally or whatever, and he kept getting confused about this because this corresponds to relations in the C-star algebra not having to be between partial isometries, not having to be right cancellative, because you still associate to each path a partial isometry. And this corresponds to the relations you get not having to be right cancellative. And he was so used to these relations between the partial isometries in the case for typical graph algebras being right cancellative that it was messing him up and breaking his brain. I thought that was kind of funny. Anyways, this is counterintuitive. And yes, so now plenty of people have studied what happens when you weaken the conditions for a directed graph. So remember, a directed graph, you require the paths to factor and have lengths which are natural numbers. And you start with the category and require that you have this thing that tells you the length. But you can it turns out that you can really remove the thing which tells you the length of paths. And instead you just have a category which traditionally satisfies left cancellation and right cancellation. So lots of people have done research on these things. It turns out that things are less concrete, so you end up not being able to say quite as much about the C-star algebra. And that's important for this project too. There are two important things I said, but really the main one right now is that traditionally they were required to be right cancellative, but people realized eventually that right cancellation wasn't actually being used anywhere in their math, or if it was in places that could be easily repaired. And so one of the professors at ASU, Jack Spielberg, wrote a paper back in 2018, I think, where he showed how you would define C-star algebras for these categories when they're only necessarily left cancellative. So because ordinal graphs are automatically left cancellative with this definition, I actually didn't have to think hard about how you would get a C-star algebra. He already proved exactly how you should get it, and like proved a decent amount of things in full generality. The other important thing I mentioned is that when you remove the length, like these researchers did, you get something a lot more abstract, so you aren't able to say as many concrete things about the C-star algebra. So what I'm doing is reintroducing the length, but instead of having the length be natural numbers, I can have the length be ordinals. And this is making things a lot more concrete, and it's also new because these things aren't right cancellative, it's left cancellative. So basically I enjoy the fact that things are more concrete in this situation, and it's what's making the project a lot more tractable for me than it would be if I was doing something, if I was trying to study just the categories of paths in general. Okay, so this is my last slide. I'm just giving you here an example of an ordinal graph. Now, when I first was thinking of these things, they were very, very hard to write down, but eventually I came up with a nice strategy for writing down some of the more common ordinal graphs. So here I have one vertex. The dot still represents a vertex. In this context, a vertex is a path of length 0. Okay? Now, I have an arrow and a label E, and then an arrow and this mysterious label. If I just have the letter, that means edge. So E is a path of length 1. Once you have all the paths of length 1, you know how to get all finite paths, because every finite path can be factored as paths of length 1. So you don't need to draw paths of length 2, 3, 4, right? You just draw the paths of length 1. But if you have a path of length omega, all of a sudden, omega is not a finite sum of finite ordinals. So I can't write a path of length omega as a finite combination of edges. So not only do I have to write the paths of length 1, I also have to write the paths of length omega. And here I've drawn a path of length omega. I've drawn it as a separate arrow. I've labeled it F. In this colon E bar, what does this mean? It's telling you how F factors. So basically this means F ends in infinitely many edges E. So if you were to factor an edge off the end of F, so you would factor off the edge E and you would be left with the same path F. For intuition, it's important to think of these infinite paths. They always end in an edge, and they always end, if they're bigger than omega, they always end in something in length with length omega. They might not start with an edge, though. That's the direction in which you should be thinking about how these paths go. It's not that they don't end in an edge, it's that they don't start with an edge. Okay, so this notation means you repeat F ends in infinitely many E's. And since it ends in infinitely many E's, you really shouldn't think of this arrow as disjoint or separate from this arrow for E. Really, this path F is starting at this vertex and then doing something mysterious and ending by circling around E infinitely many times. But this is the only good way of notating that I found. So really, this path and this edge aren't really separate paths. E is a part of this path F. So basically what I've described is the fact that when you take F and you adjoin the edge E, you get F back. So you have this relation EF is equal to F. So this is an explicit example where the ordinal graph is not right cancellative, because if I canceled an f on both sides, I get E is equal to this vertex. This path of length 1 is equal to this vertex. That's nonsense. Now, one cool thing, if you, instead of labeling it as f, you label this as omega, and instead of labeling E as E and instead labeling it as 1, then instead of having EF is equal to F, you can have 1 plus omega is equal to omega, for example. So you can think, in that case, you can think of path composition as ordinal addition. And then you get, because of that, this graph I've drawn is actually isomorphic, which basically here just means same structure. I could formally define it, but I don't feel like it here it's necessary. This ordinal graph is isomorphic to this half open interval of ordinals. So all the ordinals which are greater than or equal to 0 and less than the ordinal omega squared. And this is an explicit example where you don't have right cancellation. So basically what I've done is I've realized that you can still think about C-star algebras of ordinal graphs. So I've done this using that professor's paper, and actually these ordinal graphs turn out to be extremely nice left cancellative categories that aren't right cancellative. They're basically like the nicest left cancellative categories that aren't right cancellative you can have, it turns out. And I've read his paper and I know how to make the C-star algebras out of these things. And a few weeks before the conference, I found some very interesting structure behind the C-star algebra. Long story short, you take powers of omega and you look at all the paths which have length less than that power of omega, and you get those sub-collections on their own are also ordinal graphs. And there's a very strong relationship between the C-star algebra for those sub-ordinal graphs and the C-star algebra for the bigger graphs. So that's what I'm working on. But it would take me a long time to explain that in more detail since this has already been going on for a while. So that's all. That's what I've been working on. This will hopefully be my thesis.
Yay.
Any
Thanks,
questions?
Ben. Thank you, Ben.
What was it?
I will say, this has made me, I will be honest, I have an analysis textbook on my desk at work, and I used it as a motivation because I'm like, imagine how much rougher life would be for me if I were in a math PhD.
Oh no.
This is not intuitive at all, Ben. I'll be honest, I'm very impressed that you can. you.
Well, basically, mathematicians just gaslight themselves into thinking a bunch of things are intuitive. So that's probably what is being reflected here.
That's probably part of it, yeah.
In my opinion, this, more than anything, I think, that I've seen, would help me get into math more.
Yeah, right? Like, I try to explain to people why math is creative, but, like, you have to, like, show it to people, I feel like. I did my best to sort of show this.
Most math things I've seen didn't make me as interested as this, if that, in my opinion. It's very cool.
Thank you.
Can you hear the fan in the background?
No.
I don't think they can. I think that the noise canceling whatever is pretty good on Discord.
Yeah, Discord's got that crisp.
Yeah. In my recording, though, you're going to be able to hear the speakers because I wasn't able to get my my headphones working because the stupid noise canceling button is broken now after connecting to my new phone. I still haven't been able to fix it.
Yeah, that seemed annoying.
Yeah, what do you think, Maddie? What do you think of the last like 10 minutes?
Pretty,
Missed all
it
the
was
prep
pretty
work.
good. I think you added extra to it that I didn't get to hear.
I added
Like
extra.
you didn't. I feel like you added more than last time I heard.
Oh, you mean when I was talking, when I was trying to explain it to you in the car?
Mhm.
Yeah. Well,
Wait,
I
Maddie,
definitely
aren't you,
added
like,
all of
in,
this
like-
stuff. All of this. You missed the crash course on quantum mechanics. It's too bad.
You're in advanced calc already, right, Maddie? If I remember Ben
Yeah.
saying to me before.
Yeah. I don't
Like
know.
calc 3 already?
No.
Oh, not 3. Okay.
Well, that's
Are you
good
gonna
for
get to
Maddie.
take?
You know,
I don't know.
Are you gonna get to
Maddie,
take
what grade
calc?
are you in?
No. I'm junior. Gonna be senior.
yeah. Because if I had a sibling that was explaining operator algebras. I'm forgetting the word. But if I had that happening to me in a car, I might open the door and jump out. Not this
Well, I wasn't
presentation.
explaining operator
Oh.
algebras. I
In
was
a car.
explaining ordinals. Ordinals are the cool thing. Look at this picture. This is
Yeah.
awesome.
Yeah,
very
it looks
cool.
like a seashell.
Yeah.
I just feel like when I was a junior in high school, I wouldn't have been close to understanding this.
Yeah,
Oh,
I was
that-
really
that
stupid as a
is-
junior. Actually, now that I think about back to this, like,
I'm
And
still
yet you
struggling with
understood the
it a little
Karo
bit.
Khan.
Me?
Yeah, didn't you play Kara?
No, I didn't play Karo. I was an
Oh.
Also,
E5
Jordan's
loser.
not the one that said they're stupid as a junior. Or maybe you both know.
Ben said that you wouldn't necessarily have understood everything in this presentation if you were still a junior in high school.
Well, I'm not
If
claiming I
you're
did
saying that you
understand
understood
everything.
then
but
I'm super impressed, honestly. But
I think I got
Well,
yeah,
most, but not
literally, Jordan
all.
already knew all of that, so just a big waste of his time to tell him all this.
Okay, shut up.
So
I
haughty
did
you
take
are,
quantum, but when I took quantum, it's a very different lens than this quantum. So.
Oh
you know.
yeah, I'm glad then that you're able to see it through this perspective, because this is like, I don't know, this is like with quantum mechanics, somehow like the more abstract way of like thinking about it makes things a lot clearer, I think. Like maybe it makes things more mysterious. Things aren't as like
I
concrete.
think this is that math
but...
major like gaslighting thing again, Ben.
What is this?
Well, I mean,
What
at least like I can
That's-
describe
oh.
this stuff without just like computation, right?
Right.
The fact that like I've been trying to learn how to use quantum mechanics as a crutch for understanding C-star algebras, because I figure that like usually the physics guides the math. Like a lot of math was discovered just because of physics. Not always, but you know. And
Ben, have you seen those
probably...
like YouTube shorts where they have Subway Surfers playthrough going on while another video's playing?
Yeah.
Yeah, I tried that trick. It did help today.
Did you understand enough to be satisfied?
Yeah, especially when I had that Subway Surfers going.
Okay.
Maybe you should try that when you teach. Like
I think so.
Have Subway Surfers on
another screen.
Oh my god.
on the projector.
That shit looks like brain rot to me. I don't know how people do it.